Hi everybody. Today we're gonna talk about how to use the very abstract concepts convolution and cross-correlation in our real life. Let's get started. In this video, we will introduce what's convolution, cross-correlation, how does our computer smooth a digital image by convolution and match a template by cross-correlation. There are mathematical definitions of convolution and cross-correlation of function f and g on the board. Both convolution and cross-correlation are operators. They are very similar from the math definition, but convolution is like mixing two functions together and cross-correlation is to test the similarity of two functions. However, how do they mix stuff together and test the similarity? Let's use graph to illustrate that. Firstly, let's draw the graph of two series hn and xn. We can see the definition of convolution of two series hn and xn on the board. Now let's draw the series of xk on the left of the board. Then we flip it around y-axis to get x minus k. After that we shift it along x-axis to get xn minus k. We can shift more. In this case, it shifted too. When it shifted more and more, let's just say when it shifted n, the convolution is the sum of the pointwise multiplication of hk and xn minus k. Now, let's go back to see the convolution of two continuous functions ft and gt. If we divide the continuous curve into numerous dots, intuitively we can regard them as series. It will make more sense to us if we regard the convolution of continuous functions as convolution series, but each term is infinite close. Now let's see what's cross-correlation. Cross-correlation is very similar to convolution. The only difference is for cross-correlation, the moving function gt does not need to flip around y-axis. It is the tiny difference that causes the cross-correlation, and convolution have totally different usages. Now, let's talk about two-dimensional convolution and illustrate how to smooth a digital image by convolution. We know if we use Gaussian's function to convolve with delta function, the new function will be smoother. For 2D image, we regard every dot in a pixel is a delta function. We can convolve the Gaussian function with the delta function by moving it pixel by pixel. Now we can see the image is much smoother after Gaussian's convolution. Now we want to know how does our computer do this to an image. Firstly, we need to know digital images consist of numerous pixels like the diagram on the board. Each pixel has a number. Bigger number means brighter color. When computer does Gaussian convolution, it uses a Gaussian kernel to convolve with the original image. Let's do an example. If we want to know what's this number in the pixel after convolving, we can use 1 times 6 plus 2 times 7 plus 1 times 20 plus 2 times 2 plus 4 times 4 plus 2 times 8 plus 1 times 1 plus 2 times 3 plus 1 times 4 and divide by 16. We just move our Gaussian kernel pixel by pixel to convolve with the original pixel on the image and get the new number for each pixel. Then we can get the new image. The new pictures will be smoother. We also call this Gaussian filter. Actually, we may use this every day when we edit our pictures on Instagram. Some people like using this to blur their acnes to make face smoother. Now let's move to the cross-correlation. If there are two sine functions only differing from the initial phase, the cross-correlation graph of these two functions will have a maximum peak at one moment when they two completely constructive. That's because, when peaks are aligned, they make a large contribution to the multiplication product. Similarly, when troughs align, they also make a positive contribution to the products. We know how to cross-correlation test the similarity of two functions. Now let's use the same theorem to match the template with a huge map. We let the number of white pixel is 1 and black pixel is -1. If one white pixel matches with one black pixel, the production is -1. That's to say, the sum of the pointwise production will arrive the maximum only when all pixels on the template correctly match the pixels on the map. Then we let the template slide pixel by pixel on the map and calculate its cross-correlation. The cross-correlation graph will has a maximum peak when our template find the match. The peak spot is where the template is on the map. We also can use the cross-correlation to find the site of a template from a noisy picture. Convolution and cross-correlation also have many other very useful functions that will be showed in my next video.
Thank you for watching. If you like this video, please give me a like and subscribe it.